operating environment and solution system that we could deploy in this area. And it came out of necessity. We started our thesis as a company, really going out there and really looking at how can we take this, what was still in the lab technology, and look at the uses of it in industry, with government and big problems that are out there, and try to find what are the quantum solutions that might have near-term or medium-term tractability. And then taking these and trying to deploy them in a way and see how they were going to scale and how they were going to work, and answer some of the questions that we had, like, is it going to take 153 qubits or 247 or 1,000 or 1,000,000 qubits to do something useful in this area? To answer those questions, we realized we need some tools to be able to go and deploy on these systems, and we'll talk about it and some of the necessity of that. Because at the end of the day, the problems are still a lot of the problems we're trying to solve have some classical basis in them. You know, you're still using data, you're still storing these on classical data systems and collating data. And to visualize quantum, you don't look at things in superposition unless your eyes are crossed, right? You still have to visualize and post-process things on a classical system. So that's complicated. And as the qubits go up, it gets even more complicated. And we realized when we were trying to do these initial jobs for Fortune 100 companies that the tools weren't there. You know, we're doing a bunch of Python tasks and linking together a bunch of frameworks that are out there. I can name some: Circ with Google, the Qiskit framework that IBM has, Pikewill with Rigetti, and they all have different data structures, different ways of talking to each other. They have different features and this, and none of those are linked. Never mind all the different backends. Are you running your stuff on AWS or Azure or your own on-prem system? Do you have some kind of Slurm drop in the back on HPC? And all these systems kind of had to work together. And we were gluing them together like we were in the lab with a bunch of Python scripting, and then throwing them in an ad hoc database, and then doing what everyone does, and then trying to visualize them using, you know, whatever matplotlib or whatever we had, or some Jupyter notebooks, and doing that as ad hoc, and it just wasn't working. So we, as a company, tried to create a set of tools that would help us move this forward, both from an academic perspective, but also commercially, to allow us to answer these questions at scale. Like, how would you really answer the question of how many qubits do you need to do some job that is even equivalent to what you're doing on a classical system today? That may sound trivial, but it's not, because the whole formulation of the problem is different when you solve it on a quantum computer, and you can get into some of that, the formalisms of how that's different. So we had to go create this solution side on the right to be able to actually do the stuff that we wanted to do on the left, which is to try and hopefully bring this stuff to practical working solutions where we can actually use this new type of hardware that's coming online. So next slide. So really, we're working, Yudong and I and the company, at the intersection of a lot of these different people who are in this ecosystem now. And that would include the research community from whence we came, which is generally the physics and the quantum information science and computer science backgrounds that people have, where they do PhDs in this kind of stuff on quantum computing. Also some electrical engineering work on the back end, on control planes and this kind of thing. But that research community that generally has come out of national labs and universities around the world. And software people who are actually working on trying to make software systems for this. We mentioned some of the frameworks like Qiskit, the folks at Google have some things. And the actual hardware, there are now companies, in addition to labs like the Lincoln Lab, who have created this kind of hardware that we can now actually work on now, real qubits, that you've seen actually in working form now. IBM just ran a couple of weeks ago 18 billion jobs over 4 days. So even the operational level of being able to do this in a data center is getting better and better. Not to mention the power of these computers. You look at Google's machine in this hyped or overhyped or underhyped, whatever your viewpoint is, and we'll talk about that a little bit today. Supremacy experiment, you know, they were able to do some things that haven't been done before on some real hardware. So those hardware partners are out there. And there are new architectures emerging all the time in that ecosystem. We also have these enterprise partners who want to use this stuff different chemical companies, people doing logistics and operations research, and really government people. People want to simulate very complex systems, something like COVID and what that can do to an economy, trying to simulate these kinds of events in very complex systems. So there are a bunch of mathematical problems that we all want to solve. And really, it's at the intersection. We're very fortunate, I think, in our company that we have to play with all of these people where we are kind of in the middle of this. And so I guess that gives us a kind of unique perspective that hopefully can generate some discussion about the ecosystem and generate some questions and discussions here today. So that's really, the context. So we're working with pretty much everyone in that sector because we're working with those enterprise partners to create software that will run on that hardware and working with the research community to do that. Next. So why are we here today? Next slide. We can talk about this. So we talked about these dichotomies. So dichotomies happen when people take stances, strong stances sometimes. And in new fields, people will get very categorical sometimes, and depending on where their background is, right? If you're someone who did complexity theory, you think that, well, it has to be MP or it has to be this before it's important or something like that. And some of you may have seen some of the, I think in good jest, sparring that happens over the quantum internet and quantum Twitter, actually, hashtag quantum Twitter if you want to check it out sometime. Some people coming from different academic backgrounds and different commercial backgrounds who are working in this space kind of spar back and forth, they'll take some stances. Like maybe some of you have seen, Scott Aronson, who I respect greatly, has taken some very strong stances based on his, category theory kind of background and complexity theory background that he brings to this. And it's a great perspective. But from other perspectives, you may take something, a different perspective on stuff. And Yudong will touch on some of that today. But it leads to some people taking very, very strong statements that you'll see out there. We need a quantum programming model that abstracts away the hardware, so you don't even have to look at the hardware. Well, not really, because in the early days of computing, you kind of had to know whether you're working with vacuum tubes or not, and that's kind of where we are now. Or quantum computers without error correction, without fault tolerance, can do nothing, absolutely nothing. It's not even worth it. Don't do it. Or some things like, well, you need to have an exponential asymptotic advantage, or don't even bother. Constant factor improvements and speedups, they're not even worth working on. And some people will say that and say it very strongly, and then show a bunch of academic papers to back that position up. And quickly it becomes like Republican versus Democrat type of discussions on the internet in a way. But like all things, politics, religion, all of these kind of things that get controversial like that, the truth is, the scientific truth is, it's somewhere in the middle, right? Maybe leaning more truthful to one side or the other, depending on the context. But the truth is, the world is analog. It's a gradient. And today, hopefully, we can bring some of these false dichotomies that have kind of occurred out there to light and show how they exist more on a gradient. That, it's not really fault tolerance or NISQ or error correction or not. The world isn't so black and white. That's not the way anything really works in the natural world or in computer science and technology. There's always a gradient of development. Some step functions will happen. Some things are very much necessary. But we'll show you that we hope that things are much more nuanced than that. Next. So here's an example. Why can't we be black and white about things? Well, it's all about quantum computing or not quantum computing. Or, well, it's classical versus quantum and speed up versus this and that. Well, the truth is, that quantum computers and classical computers will always have to work together. Even on a fault-tolerant quantum computer where you do a lot of your calculations on that thing, you still have to look at the things. And so when you look at the answer, it's going to be reduced with a digital quantum computer to a digit at the end of the day. And you're going to have to view that on a monitor somewhere to make sense of the data, because a human, like I said, can't really look at things in superposition and make sense of it, right? You don't look at a wave function. The truth is, here's an example here of VQE, which is a very famous algorithm that Alon and Yudong's lab was very much in the forefront of creating. And this variational quantum eigensolver, which is used in chemistry, in our implementation at least, involves 28 different containers and computational assets that get passed one to another, objects, if you will. And of those 28 containers we used to run this, some on this machine, some on that machine, and whatever, only one of them, the little pink cloud on the right there, is quantum. That's your quantum circuit. The rest of it is pre-processing and post-processing. So it's really, really oversimplified to say quantum does this, or classical does that, or quantum beats classical, or quantum can do this and classical can't do that. When in truth, you have a complex system that is designed to make a solution that can actually deliver some value, whether it's in science or in business. And this is what the mess really looks like when you get down to the nitty-gritty and you try to do something with it. So, you know, some ways the categories and categorical thinking helps us to illuminate problems, but it really doesn't help us to create solutions. Really, when it gets down to it, it's much more complicated than that to do the work. Next. So we think we'll be making progress, even if the categories aren't there. You know, things are not certain. Is it going to be 2 years till we have an advantage, or you know, was it good enough that we had this advantage last year with supremacy? Are we really in a supremacy regime or not? Well, you know, we can try to simulate those the swap gates that Google used on a classical computer. Haha, we beat you again. You know, things aren't black and white even on that. You know. So these hard choices, saying false choices in some ways, can be helpful, like I said, to create some illuminating discussions like how important is fault tolerance? When is it appropriate? When do we need error correction? For what, right? But regardless of whether or not that happens next year or 2 years from now, the community will still push forward. You know, I always like to bring out the analogy of 1903 with the Wright brothers and the first flight of an airplane, if you could call it an airplane. And there's, you know, some argument out there that the quantum supremacy experiment and the paper that John Martinez's group did with Google last year, that they announced that wasn't really supremacy. You know, it wasn't, the airplane didn't fly. It's not a flying airplane. You know, and that's what it kind of sounds like. No, it didn't do anything. It just did something small. Well, if you look at the airplane example, you know, it only flew in North Carolina 600 meters. That was it, right? And it didn't go very high, right? So you could say, legitimately maybe, that wasn't an airplane because it did controlled flight, but it didn't fly over a mountain. It didn't go over the ocean. It didn't really do anything useful. You know, a horse is still faster and more reliable than that airplane, right? And it's still, a car can get you over the mountain better. And you can probably swim further over the ocean with without that airplane. So maybe it wasn't even an airplane, you know. But 15 years later, you know, World War I happened, and if you didn't have an air force, you were kind of screwed. So, you know, was that an airplane or not? Well, it was controlled flight, and it was the beginnings of the idea that, yeah, you can have controlled flight. So that's a significant milestone. So from that perspective, being able to do something that a classical computer couldn't do easily, and whether it was 2 days in IBM's view versus 3 minutes, or 5 days or 500 years, it really doesn't matter in some way because you did the 600-meter flight of the airplane. And that kind of progress, you can say it's limited progress, but it's progress. And if you look even at the where we are in aviation from 1903 to 1918, wow, big difference, right? And that's the kind of curve of acceleration that I think we're on here in this field. And so I think it's instructive to look at those other historical analogies in technology to say where we are. It's not so binary. Even the airplane thing, you know, there were people saying, that wasn't a real flight. These airplanes will never be useful. They'll never fly over an ocean. So you can be categorical like that. And it's a great stance, and it makes for great Twitter conversations and arguments and whatnot on social media. But really, regardless of what your stance is there, we're pushing forward. People are investing. People are doing this because there is progress being made. Will we get to the end of the rainbow? Probably. When? I don't know. But it's really not an if-then type of a decision here, I think, you know. So next. So with that, I'll turn it over to Yudong to talk about some of these technical aspects of these false dichotomies and categories that we have out there right now.
Sure. So before diving into my part of the slide, I just want to add on a little bit of what Christopher was referring to about the analogy of quantum supremacy versus the Wright brothers flights. There are companies, there are hardware companies that we've been in contact with that is accomplished the quantum supremacy milestone. They just didn't publicize it, and I think a lot of the hardware companies are not using quantum supremacy per se as a milestone for quantum usefulness. So I think a lot of this has to do with the focus of a particular hardware company. Google is unique in the sense that they identified this very specific benchmark, which they call quantum supremacy, and then they're able to demonstrate it. And then there's a very strong scientific case for which you can argue that this is something post-classical, but it's not necessarily a useful task at all. The quantum supremacy experiment per se, it amounts to essentially generating a specific type of random bit strings, and it's not clear at all how practically useful those random bit strings are in practice. But there are very rigorous arguments that one can make scientifically about the fact that these random bit streams are indeed hard to generate classically. It takes 200 days or 200 years or 2.5 days. But there are other hardware companies that are more focused on, say, how to build systems that can solve actual problems that are potentially better than classical counterparts. And this is a territory where the comparison isn't that clear-cut as to the case of quantum supremacy, where you can mathematically argue why this is hard. In most of the real-world applications, the problems are probably so complex that it's hard for one to write down a math formula to say that here's a precise reason why it's hard or why it's easy. It's always the empirical observations that drives the algorithm innovation, and then based on these empirical observations, we have strong reason to believe that quantum computing, because it's doing something that's classically infeasible, then we should be able to gain some practical advantage. Even in most cases, it's probably a constant factor advantage. For most business applications, a constant factor advantage, twice as fast or 10 times as fast, is already driving very concrete business values. So this is also somewhat getting towards the false dichotomies that I'll talk about. But this is just to point out that beyond quantum supremacy is really the tip, the very bright tip of a huge iceberg that is currently unexplored when it comes to the business potential of quantum devices. So we sort of intentionally summarized some of the subtle points that we noticed in the past years, some of the subtle technical points that we noticed, subtle but important technical points, and we phrase them as dichotomies. So the reason why we phrase them as dichotomies is to make them intentionally seem provocative, so that people are paying attention, because those are apparently subtle but actually important points. And the first one I want to talk about is, Christopher alluded to, this sort of thinking of NISQ versus fault tolerance. So just for clarity, NISQ is noisy intermediate scale quantum devices. So this refers to the quantum devices that we have today. Those are noisy qubits. Those are not error-corrected qubits. The quantum magic, the quantum mechanical effect of these qubits last a finite amount of time, and the goal is to use that very finite amount of quantum resource to do something useful. So that's the NISQ device regime. And then there's this line of research in the academic community for quantum error correction, which has been largely theoretical, which is intended to build a set of very involved schemes for quantum computers to constantly battle against the noise and error that come from the environment. But those schemes are often so complex that people mostly believe that they're at least 5 to 10 years away, if not decades away, from being realized. So it would seem that there's an apparent sort of separation when you come across a quantum algorithm. It's very natural to first ask the question: is the algorithm written for these NISQ devices, these noisy qubits that are not error corrected, or are they intended for an ideal quantum computer that can run quantum computation indefinitely, virtually, because they have fault tolerance, because they can correct these quantum error. Yeah. So this becomes the sort of algorithm paradigms that people consider for quantum speedups, and the type of algorithm that you read about, for example, Shor's algorithm, and also the algorithms that rely on similar observations like the phase estimation. So those algorithms for which you can prove rigorously the quantum speedup are mostly algorithms that are intended for fault-tolerant quantum computers, because they typically involve quantum circuits that are far beyond current capabilities. And then recently, there's this new route, a new line of inquiry that arises in academia that focuses on what we can do with these noisy quantum devices. And the design pattern is behind the algorithms for these noisy quantum devices are sometimes very different from that of the fault-tolerant quantum devices. And it's easy to get into this illusion that a quantum algorithm has these sort of separation, it is as though if we were to plot quantum hardware on the diagram, where the horizontal axis is fidelity, namely how accurately you can execute each of the quantum operation, and vertically the runtime of the algorithm. So it is as though you can group the algorithms into these two clusters. One is for the NISQ algorithms, for example, VQE and QAOA. I'm pretty sure if you follow some of the media articles, those are acronyms that come up very frequently. And then you learn about Shor's algorithm for compromising or factoring existing encryption protocols. You learn about these exponentially faster chemistry simulation algorithms. So those are all quote unquote fault tolerant quantum computer algorithms. And it is as though in order for us to get from where we are to these ideal algorithms, some sort of breakthrough needs to happen. Some sort of magical leap needs to happen between this noisy regime and the error corrected regime. So this is sort of an illusion that is very common to have, just because of the fact that the literature is essentially clustered around these two particular types of techniques. But in reality, we notice that the physical hardware improvement is a continuous process. So if we look at the past 20 years, we have a factor of 1 million-fold improvement in this the average time in which the quantum effect lasts. So this is the T1 time, the decoherence time. Essentially amounts to the average amount of time that the quantum effect persists. So and then for 2 qubit error rates over the past 15 years, we have a continuous improvements of by 100 fold, and the physical hardware improvement is a continuous process. And for a business application, we often need not a perfect quantum computer, but we need just a good enough quantum computer for the job. And so this motivates our particular line of efforts, which is to ask can we actually develop algorithms that continuously take advantage of the improving hardware, rather than waiting for the fault tolerance to be realized, and then we can do all the nice things that we can that the academics have theorized. So we in fact investigate this particular for this very important subroutine called quantum amplitude estimation. So this underlies it's a subroutine that underlies many of the famous quantum algorithms, such as Grover algorithms and Shor's algorithms. So it's a very fundamental routine, and that also is related to many of the near-term quantum algorithms. So we have developed an algorithm in this effort that continuously benefit from this sort of incremental improvements in hardware. So just going back to the picture that we have earlier, we have this sort of cluster picture of, you know, there's a regime for NISQ where we can design algorithms for the quantum hardware that are available today, and then there's also this regime where you have a very high 2 qubit gate fidelity, and then you will get a tremendous amount of speed up. But what we discovered is that it is possible to design algorithms such that as the hardware continuously improve, the amount of speed up, the amount of acceleration you get from a quantum computer also continuously improve. So the cost, the computational cost, continuously reduces. And what we have learned are some of the most counterintuitive things. For example, we typically would think that noise and error would make an algorithm fail, in the sense that the output of the algorithm will be inaccurate. But it turns out that the noise only affects the speed of the algorithm, but does not affect the accuracy. And then there's a little bit of a Goldilocks principle, where beyond a certain point, improving the hardware is an effort of diminishing returns. So there's a sweet spot where, for a particular algorithm, we just need the hardware to be good enough. Any additional improvements in the hardware fidelity, for example, you could do extra quantum error correction to add more nines to your 2 qubit gate fidelity. But for the purpose of this particular algorithm, you actually saturate the potential for a quantum speedup for this particular implementation. So there's a sweet spot when it comes to these fidelity and also quantum speedup. And from here you can see that the sort of commonly conceptualized separation between NISQ and fault tolerance is in fact a false dichotomy, where there is no magical moment where, when you wake up in the world, all of a sudden we're in the era of fault tolerance, while the day before is all NISQ. In fact, there's only this incremental improvement in hardware and algorithms and algorithms should sort of embrace this sort of incremental improvement, rather than sort of waiting for this transition between NISQ and fault tolerance to suddenly magically happen, and then we can start exploring these applications. So this is one of the sort of false dichotomies that we want to convey, and we have publications coming out very soon, sort of substantiating these points. So you're welcome to talk with us, and we'd be happy to discuss more in technical detail how this plot came to being, for example. And the second dichotomy is somewhat more obvious to spot, and I think Christopher alluded to that also in this plot, where you have 28 steps, 27 of which are carried out on a classical computer. And so this is one of the misconceptions that at first you might think a problem is either entirely solved by quantum computer or entirely solved by a classical computer. And this is the kind of viewpoint that is that can be easily motivated by, for example, looking at Shor's algorithm for integer factorization. And in that sense, it's a great example because factoring is such a simple problem, and you can solve the core piece of it. You can solve a big piece of it on a quantum computer, and the classical computer is largely just doing some of the lightweight housekeeping, while the quantum computer is really doing the heavy lifting. But most of the real world applications will probably need classical computers also to carry out some heavy lifting operations. For example, in many cases, we would want the classical computer to take the problem and divide it into different pieces. And then there are specific pieces that can actually be solved better with a quantum computer, while the other pieces could very well be solved classically. So if you take, let's say, simulation of a drug molecule binding to a target. So those are tremendously large problems involving thousands of atoms. But perhaps the really difficult part of this drug binding problem is the very specific place where chemical reactions happen. And then what chemical reaction really is essentially a transfer of electrons. So it's really the place where the drug molecule touches the target, and the specific atoms touches specific atoms on the other side, and then the specific electrons on the atoms that are touching each other start jumping from one molecule to the other, and it is this specific portion of the problem that actually is the hard part for classical computer. And all the other sort of housekeeping work, all the other pre-processing and post-processing, the other sort of floating point arithmetics, the other logistics of how we divide the problem, how we put the solution back together when we have the solutions to the sub-problems, a lot of those can be very well handled classically. So the design pattern here really is that we use this hybrid paradigm. And I'll give you a concrete example for machine learning. So we talked about this drug discovery example, but setting chemistry aside, in machine learning, some of you may be very familiar with this idea of generative adversarial network, where the goal is you train an AI to generate data points that are virtually indistinguishable from the training data points that you feed it. So the goal is to train a generator, this G, such that it can fool the discriminator, which is also trained as you train the generator. So you can turn this scheme around and help the generator cheat, so to speak. So now, since the generator wants to fool the discriminator, and you can help the generator cheat by allowing the generator to peek into the last layer of discriminator. And so this is the modification of GAN in this associative adversarial network, where you take the last layer of discriminator, and then you learn the distribution here, and then use that as a sampling source for the generator. That way, it's the training is significantly improved. You can actually train the generator much faster. For details, you can read about it. So this is produced by a couple of our interns last summer. And the idea here is that instead of using a classical model, such as restricted Boltzmann machine, to learn the last layer of discriminator, we can turn this into a quantum, hybrid quantum classical machine learning model, where you use a quantum computer to learn the distribution of the last layer, and then use that as a sort of random number source for the generator. And this way, the high level picture is that the quantum computer is really just playing the role of a sample generator. It's just playing the role of a very specific subroutine in this hybrid machine learning paradigm, where you have neural networks that handle real world data. And this reflects this general design pattern where you start with a specific problem, and then there's an on-ramp where you take the problem and transform it in a way that is specific to quantum computing. And through this quantum specific pre-processing, you essentially bring the problem to the front door of quantum computing, so to speak. And then in the meantime, there will be some interaction between the quantum and classical components, the QPUs. The quantum processing units are, after all, controlled by some CPU. So there needs to be some kind of communication. And then the result from the quantum computer needs to be also parsed and post-processed specifically for this problem, and then integrated back. So most of this yellow, area is the majority of the existing classical pipeline for solving a problem. And what we really need to do is to figure out how to do the pre-processing, post-processing, and what kind of quantum algorithms to apply in this QPU module. And we've looked at it for multiple industry verticals. So we looked at it for specifically for quantum simulation, simulating chemicals. And this is an invited review for about the potential of quantum computing for drug discovery. We've also looked at it through the perspective of combinatorial optimization. So these are problems that widely arise in industrial engineering and logistic optimization, etc. And we've also looked at machine learning. So that's the example that I showed in the previous slide. So this really points to this the sort of false dichotomy, or the sort of continuous integration between quantum and classical. It is as though with this integration, as the quantum hardware improves over time, you have this expanding pocket of quantumness in your classical pipeline. So, so many people think that quantum computers are here to replace classical computers. I think that the more appropriate perspective is perhaps, quantum computers are here to augment existing classical pipeline, and original science will need to happen in order to figure out what these pre-processing, post-processing look like, and what this algorithm look like on the quantum device. And this design pattern persists for even fault-tolerant quantum devices, because a lot of the algorithms that you can run on near-term quantum devices are every bit as applicable for fault-tolerant quantum devices. And it's rather straightforward to appreciate it, because if you can use a finite amount of quantum resource to drive commercial value, then you can certainly use an infinite amount of quantum resource to drive commercial value. So the third area has to do with the third, I would say, false dichotomy, but it's just sort of false. You can say false trichotomy, or this sort of very siloed thinking about applications of quantum computers. So if you read a popular article, I think it's very easy to come across these three categorizations of what you can use quantum computers for. For example, quantum simulation of chemicals, and quantum optimization, and machine learning. So those are the three that are also listed in the previous slide, because it's very easy to think of it, quantum applications, as in these three buckets. But what we've noticed, a trend that we have recognized in our own work, is that this is very much a false trichotomy, and the actual picture really has all these applications blend into each other, and there are schemes where you use quantum simulation for optimization. For example, if you look at what D-Wave, this Canadian company that makes quantum annealers, you can think of it as an analog quantum simulator for the purpose of solving optimization problem. And then you can also turn around where there are problems in quantum chemistry that can be rephrased as combinatorial optimization. And there are also similar examples that you can point to for the boundary between these application areas. And then the fourth sort of dimension, I would say, or fourth aspect for this false dichotomy discussion is about the sort of programming approach, or the design thinking about whether we should choose quantum computer as a black box, or we should really open up the black box and look at the details. It seems that it's intuitive to think of quantum hardware and quantum software as two separate layers of tech stack. So I think that at a first approximation, there are companies like us that are quantum software companies, and then there are also other companies that focus on building hardware. But what we have realized that if we just sort of send quantum circuits over the fence to IBM or to Honeywell or to whichever hardware player, whichever hardware provider that we want to run our algorithm on, this type of black box approach is not likely extract the maximum value of these quantum backends. Basically, because the computational resource is so scarce, the qubits are so scarce, we need to take advantage of basically every bit of quantumness that can come out of a quantum device. And this is reminiscent of the design pattern in the early days of classical computing, where one has to be very mindful of the memory requirements of the devices, and then have to be very strategic about how to allocate different memory for different tasks, and taking into account the very details of the machine. And this design pattern is still applies, you know, here today in the early phases of quantum computing. And what we really need is for algorithms to fit the quantum hardware like a glove. Basically means that the algorithm needs to take into full consideration the strength of the hardware, and use those for particular types of application. And those usually require deep understanding about the subtleties of how these qubits are wired together. What are the gate sets that is natively enabled on the hardware, and what are the physical mechanisms that drive these gate operations, etc. And so just to show a concrete example of this type of thinking, so we recently released a study which what we call it's the application benchmark. It's the first application of the Sycamore processor, which Google used for the supremacy experiments. And this is essentially to provide a concrete sense of what it means to deviate from this black box abstract approach, but rather looks very closely at the hardware. So you take a chip like the Sycamore chip that Google has produced, and you look at what kind of gates and pulses are allowed natively on the chip. And then you look at the processor processor level layout of the qubits, and then think about for a given problem, let's say simulating interacting electrons, which is a very common problem that arises in material and also in pharmaceutical settings. And then you take a problem of interacting electrons. So this is a particular example of a Fermi-Hubbard model. It's a very well-known model in simulating materials with very difficult quantum properties. And the way we break the layers of abstraction is to take into account the structure of the problem, and then think about how to map that natively onto the processor level, and then how to design the algorithm, so the variational ansatz. So that's just the core components of the algorithm. How to design the core components of the algorithm that natively takes into account the property of these gates. And then the property of these gates also tells us what we can do for application. So this is essentially breaking all these layers of abstraction and going all the way down to the physics, and then come back and come up with this optimal scheme for solving this very particular simulation problem. And this is the type of design pattern that we find the most useful in the near term for extracting the maximum value from a quantum device. So this is all of this is meant to provide is really meant to sort of convey these somewhat subtle technical points, and you know, we try to accentuate these points by you know, referring to them as the dichotomies. But those are mostly, you know, the type of thinking if you want to extract the maximum value out of a quantum device. Often these types of dichotomies are convenient conceptual tools for a first approximation when it comes to understanding quantum computing. But oftentimes you find these dichotomies falling apart when you really try to make something happen with devices that are available today or in 1 to 2 years. So So with that, let me turn to turn back to Christopher to talk about some of the dichotomies that are not so false when you when you look at it.
Yeah, and I think thank you, Dong. And I think when we see these technical things, things get very nuanced. But what does it mean for the people who are going to actually use these computers? So if you're you know, a government agency like CDC wanted to use this for simulation, or you're a company, or you're you know, a petrochemical company using this for downstream refinery optimization, or whatever it is, right? Your problem. There are some real decisions you have to make. And when you make decisions, these actually become real tractable dichotomies. You're either going to do something or not. You're going to invest in quantum computing or you're not. And you're now forced within this less dichotomous regime that we're kind of giving you nuance for today to say, oh, well, you know, maybe I'll wait till fault tolerance. Well, you can do that. That is a real dichotomy. That is a decision. But as we're showing you, the dichotomy is not really there, but it does force upon you a time point of decision making in business or in your application to when you get involved or not, and in other ways. Let's go on to the next slide here. So when we're making actual actionable decisions based on this environment. So the first one, this is a real dichotomy, and it's not unique to quantum computing. It's every type of, you know, the Jeffrey Moore book, Crossing the Chasm, perhaps. If you haven't read it, you should if you're in technology. They talk about, you know, markets for technology, and it's really about development for technology and when does it become real. And you know, we have this kind of another false dichotomy, if I will, to add one out there, that there will be a quantum winner or there won't be a quantum winner, meaning this quantum winner, meaning that there's going to be this pause and then nobody will invest and then suddenly there'll be a breakthrough and then everyone will start investing again. And actually, that's not really something new. We don't call this in other technologies, we've never called it a winter, we've called it a chasm. And it's crossing this chasm that happens. And really the real dichotomy that exists there is whether you're in the early adopter category or not. You know, are you an innovator or early adopter? Or are you going to wait until the technology becomes mainstream and then you're going to start to adopt it? And this is really a real business decision that happens a lot of ways in a lot of technologies. And it is a dichotomy because what it does do, as we've seen historically, is produces winners and losers. You know, the people who adopted computers quickly survived, and some became dinosaurs, didn't, and they didn't survive as well. And maybe not so much of a dichotomy there, but there definitely is a difference, a differential, right? At the very least. So should you build capabilities now? Should you be that early adopter and create that expertise and create that investment now? Or should you follow this, you know, false dichotomy of, well, fault tolerant computing is not here, so maybe I'll wait for it. Hopefully, the comments that we've brought here and some of the evidence that we've brought here, and we'll be bringing more publications as Yudong alluded to show that pretty rigorously. There really is no, it's a gradient, right? So the gradient's going, and this is something that we've learned. We call here S-curve adoption. Once it hits, you can't catch up. You know, we've learned this in a bad way over the last couple of months. And maybe it can be instructive. Maybe there's a silver lining in the teaching moment that we have about exponential math and how it works. You know, we're talking about that. If you saw the graph that Yudong put there about the reduction of noise and what it does to an algorithm's performance, this is a downward exponential curve. And you know, eventually it levels out, but that curve is kind of hard to catch up with. We've learned this in the last few months with COVID. Oh, there are only 2 cases in my neighborhood. Oh, wait, there are 10,000 2 weeks later. Oh, wow, exponential is pretty fast. You know, this kind of curve catches up really quick. And by definition, this technology, because of the way it works, is exponential. It's asymptotic, the differential. And so really, unlike a lot of other technologies, you might have more time to catch up. This one is going to be pretty much not a winner takes all, but a winner takes a lot type of a situation, it seems, because it's not easy to develop, and we'll talk about some of the workforce and the technologies and the algorithms. There are only so many people who know how to do this stuff right now. So if you don't start investing in that, in learning and adapting now, once that chasm is crossed, that's an exponential curve. And we're not talking about the exponential adoption curve. We're talking about an exponential curve of the capabilities of the technology. And if you're not on that curve, it's kind of like, are you surfing the wave, or are you behind the wave, or are you in front of that wave and getting crashed on? So that really becomes a dichotomy of choice. Do I start now or not? And we would argue that there's a lot of evidence already mounting that getting started and being part of that early adopter piece of this chasm is probably the right decision for in a lot of areas. I won't say in every area. Every small business in the world doesn't have to have a quantum computing expert. If you operate a martial arts dojo, maybe you don't need to have a quantum computing expert on staff. But if you're a chemicals company and you know this is going to be disruptive in your area, you might want to start thinking about that. Okay, next. And part of that equation of whether you do it or not also involves IP. Now, this is kind of a chart of the little diamonds here being our actual patent applications in this area since we got started in the Harvard group. Some of those before we started the company, most of them after. As you can see in 2017 when we spun out and since. And look at the different areas. And these are fundamental algorithmic and process patents that are international patent families. Some of them have been published already and have been issued, so you can go out and start seeing them. Most of them haven't yet. So, and you get an 18-month lead in the way this works. So by the time you wait 18 months from now, you might realize that you're blocked by our patent or IBM's patent or Google's patent or somebody else's in this area. So if these are fundamental things, if you're doing differential equations, PDEs, well, that's a pretty broad area. And if there are fundamental ways of doing PDEs in a variational algorithm or a variational system that are already blocked, well, you're kind of going to be paying some licensing fees here. So when you're making that decision, there is kind of a binary thing here. At some point, you're too late and you're going to be paying a lot of money. And that works well for the people who've gotten these patents, but it doesn't work so well if in your domain area of expertise, you're getting blocked. And I say that maybe against my own interest and to say that we would like some people to be blocked in some way by our patents. But as a field and as someone who's thinking about this and growing this as a field, I think the message is deeper than that. It behooves you actually to fall into that early adopter category, to be the master of your own domain expertise, and start to work on developing this IP in this map and having staking out your own territory in this space. Next. So and this is another decision, do I invest or not? Am I early adopter or not? And based on that decision, okay, how do I do this? Do I go out and hire a bunch of people? Do I hire a bunch of yudongs? Well, first of all, there are not that many in the world, really, honestly speaking. Quantum scientists who've actually worked on these machines and done this work and come up with an original algorithm in this area for your domain expertise. There's a dearth of people. Are there more? Yes. Are we creating more PhDs in this area, or even applied master's degree people in that area? Yes. My undergrad alma mater has just started, announced that they'll be starting next fall an intake for applied master's people in this area. And so we've seen that in data science, and we've seen that in other areas. So that will catch up at some point, but they're not limitless. And you have to start thinking, well, what kind of company am I? Am I the kind of company that is going to be able to hire the A++ players? If you are a restaurant chain company, even if it's a big one, you might not, for your logistics problem that could really benefit from quantum computing, really, realistically, may not have the means to be able to get the best player to come to a McDonald's or a Burger King, even though you got a lot of money. Practically speaking, can you hire the best quantum scientists there? No, probably not. Maybe you could, though, if you're a Boeing or someone in aeronautics. You have a lot of interesting problems there, aerospace or in some other area that plays with physical systems that are really interesting to simulate, where HPC is a big deal. Maybe you can be more successful there and develop your own workforce. And we're seeing this already. Some companies have already started to decide that we need to have our own teams. Some financial companies we've seen our colleagues move to We'll move to Wall Street to look at financial systems, because these are really complex, interesting problems where the math is really interesting. So you can get an A++ player to actually move to one of those companies and hire a team around those people and start working in this area and gaining that IP. But that's not a solution for everyone. It's also not a solution for all C-suite decision makings, maybe especially in the time of COVID. If this is 5 years down the line, maybe I don't want to put all that investment into fixed costs of having a team inside the company right now. So maybe I want to work with a consulting company. You know, maybe you want to work with a, you know, a QC Aware or a Zapata or some other company that has niche expertise in this area, or with one of the larger companies like IBM or Google, or through an Accenture that might be gaining some of the expertise in this area, or a Tata, or one of these integrators who might have some of this expertise in-house and might be oriented towards your domain. That could happen. So there really is a kind of binary decision there too, because you can't kind of, you know, have a halfway there not solution for this. You either have to decide we're going to hire and we're going to be serious about this and create a real team, because people want to be around other people working in the area. You're not going to just hire one and then be done, unless that person is just overseeing all of your external consultants, in which case you're actually deciding to work with consultants and external things. So this outsource versus bring in-house is a decision. I don't have an easy answer for you here, but you need to be thinking about, if you're a company or an organization, do you need to have some of that expertise in-house? Two, because of the hardware stuff and getting all of the juice out of it, if you near-term really think you have a problem that needs to do it, to some of the other points that Yudong made about, you know, really getting all of the juice, all of the gate depth, every single qubit's worth of power out of that machine, you need someone who knows how to do that. So you need some really good expertise in-house if you're going to do that yourself. So you can't just abstract it away. That's pretty naive. So, you know, there really does have to come a decision point, a binary decision point to, am I going to hire up and get serious about that and get some really A+ players in-house and develop a team and seek out our use cases? Is this going to be disruptive over the medium term in my midterm business plan, and want to do this, or not? And in which case, okay, just leaving it probably also isn't an answer. We have a retail company customer that's very interested in optimization of their distribution, because it's their whole business is distribution, even though they have a retail product that they sell. Kind of like a, you know, it's not Burger King or McDonald's, but kind of a similar type of a thing. So, you know, even if they don't have their distribution thing, you know, McDonald's still has to get its meat to its various outlets and restaurants, right? And that costs money, and that's a big cost. So using this kind of computation to do that could be a big win. So whether they have a team or not, maybe they don't have a team, but they can come to a company like Zapata or one of our competitors or somebody else, and then try to work on that solution without necessarily hiring it in-house. So that is a near-term kind of decision that people have to make. And even if you're not going to have your team in-house, you might want to start thinking about having that problem solved and starting to work on it before you get hit by the wave. Next. And when you're working with consultants, you might want to think about whether you're developing these things based on whether you are going to be severely disrupted or not in your major business. And there are three things here that we can give as kind of tools to start thinking through this. First of all, discover what your quantum use cases are. You need to do that study. Do we have any? Should we do it? Not every problem is going to be a quantum computing problem. You know, we've had people come to us and say, oh, we want to do this. And then, you know, Yudong and the scientists are like, we actually had it's a kind of instructive example. We had one major company come to us, and they had about 6 use cases. And they brought them there, and they did nice write-ups, you know, on one page of really great thinking about what the maths are here to what we need to do. And they brought 6 of these pages. They were all excited about these wonderful use cases they brought. And 3 of them immediately Yudong and the team threw out the window. And my business development guy was like, no, we can do that. We can use classical computing for that. No, we're a quantum company. We're not going to do that. And it was kind of instructive. It's like, yeah, but those are good. Yeah, but they're not great quantum use cases. And out of the 3 left, right? So 2 of those kind of did require some fault-tolerant quantum computing, or at least better error correction, right, than what we have now. So they were kind of on the slope of, we need at least more qubits than what we have now. So the answer was, yeah, you can do that in 30 years, but maybe not today on a quantum computer. Another one was like, why don't you just use regular neural networks to do that? Why would you want to use a quantum computer to do this when there's already an AI solution that's out there, tractable today? So there was one, fortunately, left over that became actually a major engagement for us to do, and we'll be publishing some of that towards the end of this year. The first couple of phases of that work, which is some pretty awesome and important work that got done. But you have to do the homework to really figure out what those use cases are and what are not quantum use cases. Some of it's not trivial. You really have to do some work. So the whole point of being an early adopter is you get to shake that out quickly and learn what not to do and fail fast and have those learnings so that you're not wasting time and spinning wheels there. Also, if you're going to make this decision, you have to incorporate some of these quantum tools and technologies, right? You have to get your data systems in place. You can't just do this ad hoc. You're going to have some complex workflows like the one that we showed you. That was a chemistry one, but a machine learning workflow and these kind of things. If you're doing machine learning on a serious basis now, or data analytics on a serious basis, then your digitalization is probably there enough to start doing this, but there are quantum specific tools that you're going to need to start incorporating to really make this work. And work in your data centers, and think about the security protocols you have when most of the assets that are quantum computers are out in the cloud now. There isn't one that you can host in your own data center unless you're a large government or something. So realistically, you're going to have to think about how that cloud integration is actually going to work if you're not doing sensitive stuff on the cloud. So that has to happen. And then acquiring the science and engineering talent, if you've decided kind of to outsource that or not, you need to know where you're going to get it. Who are your partners going to be? If it's external, who internally are you going to do, and you need to develop that hiring plan. So you have to look at the intersection of these things when you're making that decision, really as tools. And it might be time to, at least as a project, to get that strategy going if you think that you're going to be disrupted in this space. Next. And so lastly, we have this thing about a real kind of dichotomy, because on each decision case, you're going to have to make a decision. Do you keep secrets, or do you openly collaborate? Do you open source, or do you keep it in-house? Do you keep it as a trade secret, or do you publish it to the world? And is there an opportunity for pre-competitive, let's get this out there and throw darts at it, or do I want to have stuff that is IP? Kind of related to some of the other points that we earlier spoke about, and they're kind of linked a little bit. Some of it is better to keep in-house and secret. If you're developing a quantum trading algorithm that's going to help you make more money than the next trader on Wall Street, I'm sure Goldman Sachs and JP and all these people, they don't publish their trading algorithms, and they don't patent them because they don't want them public. So there's a good reason for that, and that may be the case here. But there may be some early areas for open collaboration on things like compilers and drivers and things like that, where we feel, and we'll be announcing some coming up that we can discuss that we'd like to promote for the industry, that where open collaboration really does make sense, and reinventing the wheel everywhere doesn't make sense. So these kind of decisions are really have to be made for each one of these technologies, and they're kind of individual. But the idea that everything needs to be open is also, that's another false dichotomy, because some of these things you want to keep as proprietary secrets in your domain, and that's beneficial for you versus competition. So now the places that we have to think about this are in IP. Do we patent or not? Do we keep the domain-focused IP? That usually should remain in-house, like I mentioned with the trading thing. Or if you're a chemical company, are you going to publish all your best chemical libraries? Or a pharmaceutical company publish all their best hits and leads to everyone else? Or the clinical trial data, early stuff, ADMET properties of everything? Probably not, at least not right away. But we do need each other, as I mentioned, as an ecosystem to build on each other to develop the technology. So there may be some answers. Let's look at a historical example like printer drivers, right? Do we really want to have PostScript? There's a nice example, right? Where we could print black and white text to every single printer in the world. Yeah. But if you're Epson, maybe you want a specific driver. Okay, but do you want to be a printer driver company? Is that really a thing? Do you want to be the printer driver company and own all the printer drivers in the world? Maybe that adds value, but maybe not. Maybe having some open source types of things there, even in compilers and in areas that we can touch upon, like intermediate representations and instruction sets, that we care about as computer science people and engineers. Maybe some of these you don't want to keep recreating the wheel all the time. There was a reason why we had ANSI, and we had ANSI-C and all of these things, and macro assembly. They're kind of the same thing. We had CISC and RISC. Some of these kinds of things make more sense to be standards, and you kind of have to make that decision early in the game with these kind of things. And alliances can form, and that can happen on the technology side, but also on the user side of this. If we go to the next slide, we're seeing here's an example of Amgen and Takeda, two fierce competitors in the pharma space, joining this Quantum Leap project to, in a collaborative and pre-competitive way, leverage technologies. And they're doing this in quantum. There's actually a group that we've been in discussions with among pharma companies where they're like, well, yeah, one company just owning all the pharma-based drug, like some of the things that Yudong referred to in drug docking or whatever, everyone's going to do drug docking. Let's just get the drug docking stuff going because that benefits everyone. So maybe we can all invest and not have to take individual technology bets in that area. And this kind of thing can happen. So even on the user level, maybe I don't have to own the entire world of my algorithms. Ha 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 ha. I rule the world. Maybe that won't happen. I've said even on platforms, there's probably not the magic. I've said recently the magic ring that rules them all. That seldom happens, and usually that happens over consolidation over time. When we started out with mobile operating systems and phones, there wasn't just two, Android and the iPhone. There were different ecosystems out there. They eventually consolidated with market forces. So a lot of this doesn't happen by decision. It happens organically as people coalesce, and that will probably happen in the different phases of this industry as well. Trying to force that to happen is probably an artificial pipe dream in a lot of ways. So this is really something that you have to think about, and you have to think about it on the business side, on the technology stack side, and in each individual layer of these stacks of where you're going to have open collaboration and where you're going to keep secrets. Is open source always the best solution? Probably not, and probably not for a business, right? You have a lot of big companies who will be out there promoting that because it's in their best interest, it's not because they're saving the starving COVID patients in pick your destitute country that they're doing that. They're doing that because it benefits their business model to have everyone else in academia and everyone else publish everything and have open source because they can use their brand and their power of hegemony in the industry to own it anyway. And that prevents innovation with startups. So there are some cases in which startups and other companies, software companies particularly, may not want everything to be open source from the onset. But as I said, there are some areas where it doesn't make any kind of sense to try and create a hegemony of things like printer drivers, or in this case, transpilers for quantum computers. In our opinion, that just doesn't make a lot of sense in this pre-competitive environment. So, next. So conclusions, and maybe to summarize, we think that the dichotomies can be useful for helping us to push deeper into understanding both in the technology side and the business application usefulness side of this industry as we emerge here. And as we gain experience with the quantum algorithms, the programming, and the hardware, the truth is, though, that a lot of subtleties will become really significant, right? So we have to be nuanced, and we can't be categorical in our thinking at the end of the day. It's useful to drive discussion, but the reality is somewhere in the middle and somewhere in the gradient. Zapata ourselves are committed to staying in the forefront of these discussions. We like the debate. We're out there. Maybe some of you have seen me be a little bit controversial in the Twitterverse and whatever, and we think that's good. We want to be part of driving the discussion forward in a positive way in this ecosystem, and really push this quantum computing forward, because we really think that this is the beginning of a significant revolution in technology and how we do things. When is it going to be? That's for anyone to know. And maybe that is the one thing that we can say, that we can diverge in our opinions, but still work at the same way forward towards getting this to work at some point. And that's what we have as a discussion. I think we can start answering some of the questions that we have here. Thank you.
Yep, thanks.
Yudong, did you see any while I was gabbing away there?
Yeah, I've been answering the questions in the chat box. So I guess at this, I guess I can highlight some of the common themes and comment on it. I think one common topic is about the hybrid quantum classical neural network that I presented as an example of this hybrid quantum classical design pattern. So I showed the work of our two of our interns. That particular work was using these MNISQ digits and also CFAR image sets for benchmarking the approach, and they compared against I believe it was the convolutional neural networks, some of the more state-of-the-art classical techniques against the scheme where you have a simulated quantum device as a latent space sample generator. And I'll try to find the paper. If I exit the presentation, so what they compared is the inception score. Inception score between the different schemes. Maybe I can just pull up the PDF and talk to it directly. So there's the Boltzmann machine. There's architecture details. This is stuff I covered in the slides. So this is the plot where they compare the quantum associative adversarial network with some of the classical benchmarks. So this is a direct convolutional GAN, etc. So generally, the higher the inception score is, the closer the sample is, the more authentic the generated image is compared with the training image. Let me see if they have actual pictures. Yeah, so they have actual pictures that's generated from the hybrid quantum classical neural network. So here, the quantum computer, it isn't really generating the image directly. The quantum computer is really sitting deep in the latent space, in this latent space, generating low dimensional samples, and then it's spitting out these bit strings, which will eventually be transformed to these images. And it seems that there's, if you squint your eyes, maybe there's some minute advantage, but this shows that with this hybrid scheme, you can have a performance that's on par with some of the state of the art. I just say one of the caveats of this type of result is that first of all the inception score is, some people contend that it's not the best score for measuring the quality of image. So a lot of these machine learning applications depends on what kind of quality metrics that are being used, and also this type of performance could be outperformed, let's say, with a larger neural network, for example, or a model with more parameters, or a slightly better training method. So this is really the territory where you're comparing heuristic algorithms against other heuristic algorithms, which is perhaps not the kind of territory where, for example, Shor's algorithm has a sort of unambiguous speed up for a very well-defined math problem, and it's there are very concrete proofs that you can write down and say this is a polynomial time algorithm, while all the other classical algorithms are exponential time. This is one of those sort of areas. One of those situations that are very common across different industry applications where you're comparing different heuristics. Let's see, there might be some messages coming in real time.
I think we can answer one of them, Yudong. There's a kind of cool question about chemistry and what will be the first application of this. I think it's also a very nuanced question. This is also not very binary. Let's talk first about first principles chemistry, quantum chemistry, because that's what everyone talks about is modeling, or this docking problem, or these first principle ab initio types of things. The truth is there. Everyone says, oh, chemistry will be a big one. Yeah, it is. These are very difficult quantum systems to model. The problem is that they are difficult ones to model at full accuracy, right? What we'll talk about is, full CI accurate representations of these models, with complete basis sets and all of this. That's going to take time because we need a lot of qubits to do that really, really accurately. And the truth is, some of the classical approximations that we're doing now using classical hardware are pretty good. You've mentioned a few here, and they're really good. And to really get better accuracy on big enough a system where it's going to be much better than what we have in the classical system today is going to take a little bit of time. How much time? That is actually nuanced by the size of the system, how complex the system, how entangled those systems are, correlated those systems are. So there's no real answer for that unless you look at the actual chemical problem, but it's going to take time to do ab initio chemistry better than we can do it with density functional theory and some other different models that we have and other different tools we have in classical computing for quantum chemistry. That's the truth. Does it mean we shouldn't work on it? No, because like we were showing, there's a quick slope there, and we're getting closer to doing some of that. And there are ways of making the problem more granular by grouping things and taking only the piece that's really quantum, really only these really highly correlated systems, and really looking at that piece and only having that done on the quantum computer and doing the rest of it in classical approximations is one way of also attacking the problem. So even that's not really a binary type of thing. So no easy answer there, but ab initio is hard, okay, in general. I would say also that, but there are other areas of chemistry that may be also, we're seeing here the machine learning pieces that can also be applied in chemistry in areas that may be tractable more on the near term. For example, in generating chemical libraries, using these generative models that we're talking about here, that can take advantage of quantum properties that are not as easily represented or tractable in classical computers. To create generative adversarial models that might generate new possibilities for synthetic compounds and these kind of things that we can use, or in screening chemical libraries for certain quantum properties. So this kind of quantum machine learning aspect of it may also be more tractable quickly in some small area than the ab initio types of chemistry that's out there. If you're going to compare, apples to apples of when are we going to beat the classical computer at doing something useful for the chemists, for drug discovery companies or materials companies. That's not a all-encompassing statement, but I think it's a kind of comparative thing. Yudong, did you want to add to that?
Yeah, so I also typed this in the chat box. So the type of applications that we're most excited about fall under the so-called strongly correlated regime for chemistry. So those are regimes where you have electrons that where you need to simulate the states of electrons that are highly entangled, and often classical algorithms struggle to describe these entangled states very accurately. So you have these heuristics such as DFT and Hartree-Fock and all these different approximation methods that quantum chemists have been developing in the past decades, just to work around this this one sort of crippling limitation of classical computer for representing very highly entangled electron states. So if you imagine the very simplified picture where each electron has only two states, so each electron is like a coin, and then 50 electrons certainly doesn't sound like a very big molecule. For example, the carbon dioxide is a very small molecule. It has only 3 atoms. It has 44 electrons. So a molecule with 50 electrons, it's certainly a very small molecule. But imagine each electron being a coin, and then to describe the entangled state of 50 electrons, that's 2 to the power 50 little complex numbers that the classical computer needs to keep track of, and that is a very overwhelming amount of information. So 2 to the power 50, that roughly translates to at least petabytes of disk area, disk space. So that probably you'd have to use some of the largest supercomputers on the planet with some very careful engineering to really do ab initio simulation of 50 electrons, a problem which is very small, considering the size of the molecules that people are using for materials engineering, for drug discovery, and for all the practical purposes. So this is where quantum computers really come into play, and part of the excitement about quantum computing in the scientific community for the near-term devices is indeed to be able to model these very complicated electron states in ways that classical computers cannot.
So there's another question here about formal languages, computer languages, and Q# was mentioned here. And the question is there industry interest in developing languages? I think the answer is yes. You saw Q# there and whatnot. But I think that, a lot of the formalisms can be also described in Python. So we're using Python, for example, or other modern languages to create some of the abstraction level at the language level that allows us to do operations at the quantum level. So is that really the gating thing, to have a language that does that high level abstraction? No, we can really use the power of all the other tools on that high level of abstraction that we've developed. We're standing on the shoulders of giants in that way. I think that, and Yudong can comment further, I think that the bigger challenge is what you do on the level of compilation and how you take instructions and you divide them between what runs on the quantum computer and what runs on the actual the classical computer. And then further in the quantum computer, what are the different control modes? What are the different feedbacks and this kind of new mode of hardware? Putting that into a language that runs in Python is really not the problem, but on a low level control thing, there's a lot of work that still needs to be done. Yudong, did you want to add to that and add some color to it?
Yeah, this is one of those things. So low level software is one of those things that we as a software company in quantum space has been particularly sort of bottlenecked by, I would say. We're running into all kinds of issues with Qiskit, with Q, much less so with Q#, just because of the design methodology. The bottom line is that each hardware provider or each quantum computing player, this big corporations such as IBM, Microsoft, Google, and also startups such as Rigetti, etc. There are different paradigms that each of those companies are trying to advocate for, and those paradigms are comes in with different strengths and weaknesses, and then they don't necessarily they're not necessarily interoperable. And the situation that we're faced with has been that we have, we found really useful packages in library functions in Qiskit, but then there's also this little nugget in the circ in Google that is very useful. And then there's also we find this instructions set in this PyQuil framework, which is promoted by Rigetti, very useful. So we find little nuggets everywhere, but we need to find a framework that somehow makes all of them interoperable. So this is the motivation that allowed us to build this workflow management system called Orchestra that we're promoting this year. So our viewpoint is that the field needs to converge to some kind of standard. So the kind of standard that is already established in the classical world in terms of the different layers of abstractions. So if you ask a classical compiler person, right, so there's no ambiguity as to what each part of the compiler, which level of abstraction it sits in. So you start from source code, you have the front end of the compiler that turns the source code into this intermediate representation, and then you have further processing that turns the intermediate representation into the hardware-specific assembly language. So it could be x86 or ARM. So the classical compiler world is very well established and with very clear layers of abstraction. For quantum, this is still an early stage where different people have different ideas, and they have different proposals for the best practice for programming a quantum computer. And our approach has always been very pragmatic, because we need to make sure that we deliver on time to our customers. So if someone has a solution that is already that checks all the boxes, then we will spare no time jumping onto it and adopt it. But the issue is that right now there are still these holes in the tech stack where no one even recognizes these holes as problems, just because there's already a very diverse set of approaches that people are adopting, and we really the field really needs sort of a standardization type of efforts where people can pull their heads together and figure out what are exactly the holes that needs to be patched up for this entire tech stack to work. And someone in the chat box also asked about the Quantum OS initiative. I think River Lane was spearheading that, and there was recently a very big initiative from the UK government to build a quantum operating system. Our viewpoint is that we already have pretty good operating systems from the classical computer world, to manage the processes, to manage the memory, to serve as all kinds of sort of bookkeeping and logistics, logistic management functions. And for quantum, we really need to take one of the existing classical operating systems and think about modifications to this existing operating systems, and think about what are the changes that you need to make to the process manager so that it takes into account that this process involves quantum computing. So for example, the near-term quantum devices, because the qubits are very fragile, so you cannot, for example, an operating system should not treat a process running on a quantum computer as a normal process where you can do context switching between multiple processes. The CPU cannot sort of take for granted that a process can just be interrupted at any time, and then you push the results into the stack, and then you context switch to some other process. So you need to modify the OS to be mindful that a process is running a quantum device. So you need to somehow implement the right kinds of flags and then modify all the layers of the OS accordingly. So that's the type of sort of pragmatic solution that we believe is the most fruitful way forward. But getting back to the sort of quantum OS initiative, I think, so I looked at some of the technical specifications coming out of the popular articles, and my understanding is that it's more of a suite of low-level software tools, like building the instruction sets, building some form of software tool that allows you to directly control the low-level hardware aspects, the pulse level control, for example, for different gates. So it's not really an operating system in the classical sense. So that's why I think it's a little bit misleading to say it's a quantum OS, but it is nonetheless an initiative that will result in some useful low-level libraries, for example, instruction sets or control schemes that will work very well for specific hardware platforms.
And I think that there's some misconception out there, maybe because the people coming into this area are a lot of time physicists who don't know all the classical computer science stuff. So there's a little bit of a bifurcation there. And there's this thing called open chasm out there, which some people are referring to as some kind of an IR intermediate representation. It's not, it's an instruction set, kind of like CISC or that kind of thing, if you think about it as an analog to what we have classically. And so there's a little bit of misunderstanding about what even these layers are with some of the quantum community, and they talk about it in confusing ways, I think, because they aren't steeped in what's now actually decades of legacy of how we deal with these things in actual classical computer science. We already have these parts. And in some way, as Yuzhong's saying, and I agree from the classical side, we don't need to rip everything up and start again. We don't need a new OS or a new, some of these things. We don't need a new cloud to run cloud computing for quantum. A lot of these things are all there. We don't have to rewrite TCP/IP, right? A lot of this we don't need to redo, but we do need, as Yudong is referring to, have certain quantum aspects dealt better, even at the low level, and then abstracting those back up so that we can actually call them in higher level languages. But we don't need a whole new higher level language. We just add some statements there to be able to handle them. I think is the way to kind of think about this. We don't need a brand new Python that does quantum version of Python, for example. That's not necessary. I think there's a little bit of a misunderstanding out there that because we're in quantum computing, we're gonna have to rip everything up and start all over again from the bottom to the top of the stack. And that's just not true.
Yeah, and it's worth pointing out that the US has its own sort of similar sort of quantum consortium. So it's called QEDC, Quantum Economic Development Consortium, of which we're active participants. And this is very much one of those agenda items being discussed in those QEDC forums, where we sit in the same meeting with folks from IBM, from Honeywell, from all kinds of hardware and software players, and really discuss those issues that are common to everybody in the field. At the end of the day, standardization is really what benefits everyone, because then there's with standardization, there's this the fair partition of labor, fair division of labor, and then the field can further diversify and make progress for specific fields, for specific applications.
And this is one of the areas where, in my part of the talk where I talked about the areas where you want to open source, it's a huge thing, and you need to have all the players in the same room to really come up with a real quantum compiler or a quantum instruction set, or something lower level, like we're talking about an intermediate representation that then compiles these down to the individual classical quantum pieces. You need to have the players in the room that are developing the hardware as well as software people, and really become that sandwich. That's an area, we were asked, I think, that question in terms of, what's the competition for Zapata? I don't think that's specifically one area where I don't think we will want to compete. I think we should collaborate and have an open source standard, because it's too big for, the tens of people we have at Zapata and the tens of people that another startup in the UK have, or even all the people in IBM, or Google or any of these companies have, to really dedicate to that and do it right. We really do need to be collaborative. And the whole benefit is the network effect of the hardware company now can write to something, whether they're an ion trap or a superconductor, and pull from that to create low-level pulses that already exist from that high level, and not have to worry about what the high-level language is even doing, right? So in that sense, I think that all players win in that kind of a situation. It's pretty competitive, and we would promote, I think, the viewpoint that that's one of the specific areas where we think that collaboration makes more sense than being proprietary, because it's just too big for any one company to do. And if you do it as one company, not everyone else is going to use it, so it's not very efficient. Okay, let's see. There were some questions about really what are these correlated systems? What are good examples of those, and where might that be, really applicable? Maybe we talk about transition states in chemical reactions and why those are important. There were some of those questions. Yudong, do you want to take a crack at that?
So there are. I see there's questions about what are the what counts as strongly correlated regime. So this is really one of those fields where fundamental physics sort of meets computation, and one of the recent examples that we looked at. So chemistry, for example, chemistry is filled with these so-called strongly correlated regimes. Every time if you stop a chemical reaction in the middle, right? So take the simplest chemical reaction. Let's say if you're burning hydrogen, so two hydrogen molecules coming together, two hydrogen molecules and oxygen molecule coming together to form two water molecules. So initially, the hydrogen molecules and oxygen molecules are all by themselves, and there's a pair of hydrogen atoms that grouping together. There's a pair of oxygen atoms that are grouped together. But then in order for them to form this new molecule, there has to be a stage where all the atoms are mingled with each other, right? So where the pair of hydrogen atoms that previously formed the hydrogen molecule is sort of torn apart, but not all the way torn apart. And then the pair of oxygen atoms that previously formed the oxygen molecule that are sort of torn apart, but not all the way torn apart. And then there's this intermediate phase of a chemical reaction where all the atoms are just in transit in terms of, departing from their old molecule and forming new molecule. And this is the type of regime where the electrons don't know where to go. Because, if you're an electron in the middle of a chemical reaction, previously all the molecules are well separated. And then so for an electron, you pretty much will stay on either one side or the other. But in the middle of a chemical reaction, the electron could be both, on the spin orbital of an oxygen atom and the spin orbital of a hydrogen atom. And then, so this is the superposition state, right? And imagine the type of chemical reaction that involves dozens of atoms, and then each atom has dozens of electrons that are all mingling with each other. Then this gives rise to tremendously complicated states, quantum states of these electrons. So chemistry is filled with examples like that. The simpler place to look for these strongly correlated examples is perhaps condensed matter physics, and this is a place where the problems are a lot simpler than the type of problem that you come across in chemistry. The problems with atoms and molecules. So in condensed matter physics, for example, people study these seemingly very simple physical systems, such as, what if you just take one type of atom and line them up on a 2D grid? You just put them together like the tiles in the bathroom, and they just form this 2D plane. And it seems like the type of physical system that has a lot of symmetry, that seems very easy to simulate. But it turned out that those systems, with all its symmetry, still are among the hardest problems to crack for condensed matter physicists in the past decade, because the way the electrons are interacting with each other, it just makes the problem impervious to any of the approximations. Basically, there's no approximation that you can introduce in solving these problems that doesn't sort of throw away some of the essential pieces that are needed to describe the physics. So it seems that there's no other way to solve these. For example, 2D Fermi-Hubbard problem, I mentioned that in the chat box. Those are basically problems that look like just the same type of atoms lined up on a grid. The sort of very simple looking physical systems. Those systems are still very hard to solve, and it's hard to solve these problems even for very small problems. Let's say you line them up, you line up a 5x5 grid, and this is still this tiny problem. Imagine a patch of 5x5 atom, the 25 atoms in the material. Those are tiny, a negligible patch, compared with the size of human experience. But those are still the problems that are beyond the largest supercomputer in the world, just because of this exponential blow up as you add more atoms to the setting. So some of the most innocuous looking problems in condensed matter physics are actually really strongly correlated electron. It involves very strongly correlated electron states, and they defy the smartest algorithms that you can run on a classical computer. So those are probably the candidates that we are most excited about in the near term, because that means we can start with these very simple looking problems and see if quantum computers can solve better than classical computers.
I think there were some questions about framework and object-oriented versus functional programming of a quantum computer, and I think there may be some understanding of where the quantum processing unit sits into these frameworks. And I think that that's maybe the most important point, is that, you know, I think what we're talking about is a specialized piece of hardware in the modern environment that we're in, right? A QPU is nothing more than a fancy GPU in a sense. It's different, but it's a, you know, a piece of hardware that does a specialized task. And not every task deserves to be put on that QPU, that quantum processing unit, as Yudong was saying in his comments, and I think I alluded to it as well. Not every piece of math that you're going to do, a lot of the pre-processing, post-processing, most of it, almost by definition, even when we get to fault tolerance, will still be done on a classical computer using CPUs and GPUs to do a lot of the processing, whether you share memory or not. The different frameworks that we use, frameworks are different. Frameworks are about how do we split up our program in a way that makes it extensible and modular and these kinds of things. And there's an opportunity to do that in the way that we do this. We use workflows in Orchestra to do that, so that we can use basically a Kubernetes framework where we can run pieces of code, you know, on one piece of cloud or on another cloud, or without being agnostic even to where it's running in a distributed manner. We can run our containers all over the place. And I think that that's a useful modern framework for DevOps right now. You know, but the actual piece of code that ends up running, it can be divided up, and oftentimes it'll be part of different tasks that'll send this piece to a quantum computer, and I'll send just this function to a quantum computer. It really is, I think, Yudong, and maybe you'll disagree, but more on the functional level from a programming larger abstraction point. When you get to the QPU level, it's not really about object-oriented or what kind of framework you're using, or, you know, Corba type of federated system you're using, or whatever. It's more about calling functions to do very specific math for the most part.
Yeah, there is a sense in which, you know, quantum processing unit is similar to these other more exotic non-CPU processing units like GPUs or TPU, or I think there's also a neural processing unit, etc. With maybe the most substantial difference being the type of transformation that's needed, the type of sort of mathematical know-how that's needed to identify and also execute the very type of transformation, the very specific way you need to massage a problem into a form that is compatible to quantum techniques and quantum hardware. It's substantially more difficult than, for example, using GPU for linear algebra, or for using NPU, neural processing unit, for neural networks. I think it's fair to say that some original research sometimes is needed to actually figure out how to take a problem and optimally divide it into sub-problems that are most take advantage of a given quantum technique, or take advantage of a given quantum hardware. So there's a fair bit of sort of math that's involved in the mix among the sort of programming considerations. And as far as the specific paradigms of programming, that you know, functional versus others, I think that this is very much driven by adoption. So Q#, and you know, similar to its functional families like F#. So I believe that Q# was actually a modification of F#. So the predecessor of the current Q# was this package that Microsoft was promoting earlier, called Liquid, and the Liquid package was built essentially with F#, and I think they later on modified that and turned that into Q#. In general, it seems that as long as we have a good intermediate representation, it would seem that it doesn't matter what particular programming paradigm one uses. It's just that for some reason, you know, people have chosen Python as the primary programming language for some of these quantum programming. So Yeah, so I think that it's possible that the functional programming could play a role. Although I'm not seeing immediately what specific aspects of functional programming can work more conveniently, in tandem with quantum as opposed to the other paradigms. But I think maybe there are more sort of in-depth reason why you would favor functional programming over others.
So we've been asked to take one app and do a detailed discussion around the solution. This is where it does become one of those little proprietary things. Unfortunately, a lot of the work that we do that's real world is about real world problems with real world data. And we'd love to be able to talk about it, but the companies that pay us a lot of money not to talk about those things because it affects their actual operations. I mean, these are big problems they're trying to solve that are proprietary. They make those decisions, so we can't do that.
And Chris, I totally understand the proprietary and that piece, but if you could keep something at very high level for us to take a flavor of the solution without giving the real data or anything from that point of view. I absolutely respect that.
Yeah, I've alluded to it. It's hard to get really low level on it because you'll know exactly what company I'm talking about when I did. But, one of the things is... one of the examples is a company that has to distribute a certain retail product, like I said.
Right.
Over all these different nodes. They cover 90% of the surface area of a given country, right? And how do you get that there? Let's call it Amazon because it's not, okay? But it's that kind of a problem, right? We have this traveling salesman problem. And you do, 3 nodes or I want to go from here to here to here and then back. That's easy, right? You get to 15, it starts to become billions and billions and billions and tens of billions, even just for variables, right? And so there is a company out there. You would think that these companies all have, like even the Amazons of the world, right? That when we're sitting here in COVID and we're ordering our stuff, that they have a supercomputer. They have a Summit supercomputer, and they're deciding exactly how to get this from Seattle, ordered from the Seattle computer to get this one to move it to there, and how many exact packages they should fit of this hand washing solution and this laundry detergent onto that truck to get it onto what airplane to what boat, and have it all optimized so that it comes to your place just on time. No, it's actually a person, literally a person going, I think we can fit one more pallet of that laundry detergent on that vehicle there. It really is kind of like that.
I mean, that's true. That's true. And absolutely, as I said, anything generic, which
and that's it. That's
the
one problem. We have an actual customer working on that, and we were shocked. I mean, Yudong was really, coming in at this was really shocked to see, oh my Lord. This is done on an Excel spreadsheet. And a billions and billions of dollar revenue stream is not being optimized because it's done with very simple, non-operational, really very simple business rules, right?
And I can give you some more examples like that, Chris, on offline, where I see some companies still doing in the realm of top software companies, still doing their process internally, like from 20 years ago, even today as well.
Because it's simpler. And the truth is we didn't have the computational power to even begin to consider solving that problem. So they didn't bother. We don't have a supercomputer that can do that. The mathematicians said, forget it, you can't do it. Now it starts to become tractable. And if you've got billions and billions of dollars, right, of that problem, like you don't refer to, if you could have a constant factor speed up, you're talking about saving lots and lots of money and lots of carbon going into the atmosphere. This is really big. So this is something you want to start doing operations research about and getting traction. It's not even about quantum, but it is about this new computational modality.
This is exactly about you said in the beginning of the show, that how do we fit all these pieces of the puzzle and see where quantum makes the best fit and others still make the best fit. And coming to the similar example of what you just said, transportation management. When it comes to like my 10 orders and fitting them into one box versus when it's a truck going and fitting 20,000 boxes or 2,100 boxes into that big truck. How can one more truck make it to this box so that it can save companies fuel, cost, and everything?
I mean,
now go down to the micro level is when my one order of 20 boxes.
Absolutely. Let me give you another anecdote because I've talked about this one on stage. I can tell you the company, BASF, one of our investors, right? So we're going to solve all kinds of chemistry problems for them and whatever. They're a chemistry company. So obviously the chemistry things are very important to them and they're working in that area and they have quantum chemists. So we're collaborating in that area, obviously. But when we had to have the investment improved, I was sitting there in San Francisco in a cafe and I was there with our business development people and everyone and their CFO had to approve of the deal to invest, right? Okay. And he's like, okay, wait. This chemistry thing you're talking about here, that's an optimization problem, right? He said, well, yeah, you can think of it in that way. Oh, yeah. So that's a kind of curve fitting thing. He's like, well, I know we're going to invest because our research people in chemistry really want to do that, but can you do that for my supply chain?
There you
and
go.
we're like, well, yeah. Well, then let's do that. Who cares about the chemistry? I mean, this is a chemistry company saying that to me. And honestly, the CFO said, no, because if you can do that, we're talking about moving the needle by a significant amount just with a half a percentage on my supply chain costs or my distribution costs. You're talking about $1 billion, multiple billions of dollars, the biggest chemical company in the world, So, this sometimes it's not obvious to us as scientists and mathematicians and computer scientists looking at these problems what's going to actually have the most reality in this and what's going to actually be the shortest term real solutions. But those are some examples of what wouldn't be the most interesting perhaps from a scientist perspective. Operations research sounds so boring in a lot of ways for a lot of quantum computing people, but in reality, these are places where we can make a huge difference with this technology in rather short term, I think. Yudong, did you want to add?
Well, I think there's also a very interesting trend that we're observing outside quantum computing, where you have companies that are building dedicated hardware for optimization, like these photonic companies that are not using quantum physics, but they're building these exotic physical hardware. But they're building their hardware to the specification as if they're solving a problem for quantum computer. So there are specific ways. So this is the technical term is Ising model. I think this is what's popularized by D-Wave, where if you can encode an optimization problem into an Ising model, and we thought this is a very sort of geeky physicist type of thing where you have to map everything to an Ising model so that you can solve it on D-Wave's quantum annealer. But then what we observed interestingly is that Microsoft, for example, started using the classical program for like the programs that condensed matter physicists build for simulating Ising model. They start using that for optimizing traffic just because of this legacy mapping that was originally intended for quantum annealer. Now you can actually use the mapping for using a whole sort of quantum inspired classical tools that you can deploy today to solve a wide variety of problems. So that's sort of a byproduct of this sort of quantum computing efforts, where you see this quantum inspired, you see this growing list of classical exotic hardware approaches that are also building their hardware to the specification of what we typically intend for quantum. So then this means that we have more options in the near term to be able to solve these logistic programming problems on these classical alternatives that are that have their own advantages, being very scalable. With the CMOS technology, for example, it's extremely scalable, and there are these Japanese companies that build these digital annealers. So in contrast to the quantum annealer that this Canadian company D-Wave was doing, they build a CMOS counterparts of this annealer. Of course, it doesn't take advantage of the same kind of physical effect as quantum annealer, but because of the scalability of CMOS, they're able to scale up to far greater scale than what's possible currently with the quantum approach. So this really gives us more options in the near term to be able to solve real world problems with these exotic backends.
No, thank you, Yudong. Thank you, Chris. That was very lively. Great discussion. Thank you.
No, this has been fantastic, and thanks to the audience. Some really good questions, generating some really good discussions here, and this was a lot of fun. A lot of fun to do.
Yep. Thank you.
We're getting close to 2 hours. I'd like to limit the discussion to maybe one more question, and then we'll wrap it up.
Any burning questions out there left? If
If
not, Ed, did
if
you
there
have
is-
any?
if there is no question, I would say, when can we have you again, both of you, for a further leg of this discussion?
Yeah, we'd like to do version 2, and maybe that will be
Absolutely, yeah.
we'll switch the ratio and we'll make some real dichotomies longer and the false ones shorter, hopefully.
You address my greed. Thank you so much, Chris. Would love to do that. And I would take that rain check, and Ed is working with you, and I would love to come back for that. Yes,
Right.
absolutely. Thank you.
And we'll enjoy being here as an audience too. Thank you very much. Appreciate it.
Thank you.
Thank you.
Cheers. Have a great weekend, everyone.
You too. Stay safe, everyone. Bye-bye.
Thank you.
I think, Balaji, we have the next leg. Have Ed reach out, and we can decide for some good topic with them. Thank you.